What I'm going to talk about today is actually solving complicated problems. In essence, what I do is I transfer or almost steal technology from one area to another. And that's what I'm going to try and talk about in a moment. So what's the philosophy behind what I do? The real question is, understand what's really required. If someone comes to you and say, I need one of these, no, sorry, what do you actually want to do? What's the problem you really want to solve? Break it down into the right part of the questions. And then choose what's the most suitable method from either a technology toolbox, or it could equally be applicable from a toolbox from more artistic or social science skills. And then you come up with practical suggestions. And then the bottom line behind all this is use the simplest method you can. In other words, I want to try and enable you to choose the right tool for the right job. As an example, you could cut your toenails with a hedge trimmer. I'm going to suggest that it's probably not the right tool because it's perhaps literally overkill. We're trying to look and say, so clearly, cutting your toenails, a sharp pair of scissors is the way to do it. But there are a lot of tools that you can use. So how do we try and look at these problems and break them down? Most challenges, trying to understand big problems, it's not a single subject anymore. It's been known for some time, but it's becoming even more apparent that you need to be thinking in a much broader background. And it comes back again, ask what's really required. If you like, if I'm looking at this, what's the ideal way of doing a project? Well, the first thing that we would always do is observe or watch what's going on. And then you might try and interpret that and build a model. And then from that model, you give it a kick in some direction, you perturb it. And you say, okay, so if the model's correct, this is what I'd expect. So you then do that experiment in some way, shape, or form, modify it and put it back in. But the other trouble is with most real-world problems, they have huge scale issues. So if for the moment we just take something that's biological, it works down, to a billionth of a millimeter, a molecular size, all the way up to, 100 meters for a tree. Or if you're looking at time scales, it's billionths of a second, all the way up to millennia for evolution. And actually, if you put that all together, it's 1 with 27 noughts after it in terms of orders of magnitude. So that means clearly there's not going to be one tool, one model that will solve the whole problem. So if you're looking at any real-world problem, you need to find a way of breaking it down into bits that you can understand and then sticking them back together again. So you'd sort of go, okay, let's try this. Let's do some washing. But there's a challenge. 20 years ago, most washing was done at 40 degrees centigrade. And if you think about 40 degrees centigrade, butter, for example, is a liquid. If you now do cold water washing, clearly better for the ecosystem, saving energy, the temperature is probably down at 15 or 20 degrees, and butter has become a solid. How does low temperature washing work? Now, the way that you remove fat from material is you put something in it that breaks the fat up. That might be bioactivated. You put something on the cloth that stops it being redeposited back down again. But first of all, you've got to break that bond between the cloth and the fat. So what can we do? So we can think about building a miniature dishwasher, or in this case, washing machine. And we can use techniques that are normally present in biology where you can, what's called fluorescence, where you put a material in there, you shine light on it at one wavelength, and you get a different color back out again, and you can put different materials in that shine in different colors, so I can begin to see it. And I can use some advanced microscopy. Confocal microscopy, developed about 25, 30 years ago, enables you to take three-dimensional microscopic images. But I've hinted at a problem. We want to go all the way through my lump of fat that's fallen on my clothes. As I look through my sample, it's going to get more and more distorted. You can't look through a slab of butter because the light gets bent and scattered in all sorts of directions. So this is an example of another material. It's not very biological at all. It's Philadelphia cream cheese. And at the top, you can see it's little balls, hopefully, on the screen. As you go deeper, it's still little balls of fat wrapped with protein, but it's become horribly blurry because I'm looking through all those little balls and they're all distorting the image. But luckily, astronomy has the same problem. So if you have a ground-based telescope, they want to look at the stars. And what's in between, there's the atmosphere in between. And that's constantly moving and jittering, and that's in effect why stars twinkle. So astronomers have developed techniques where they have an optical element, a mirror, that they can change the shape of very rapidly. So if the light gets distorted by the atmosphere in one way, they can put the opposite shape on their mirror and get the correct image back again. So can we do the same thing to look at our dirty washing, which is what we're trying to do? What we do is we build a little dishwashing machine directly underneath the microscope here. So there's a microscope, there's some lasers and things in the background which produce the light, and we scan the light over and we build up a 3D image, and we've got a little sample of cloth underneath the microscope objective. And what we see is something a bit like that. You can just about make out the blue lines, which is the cloth, and then the red blobs are the fat. So that's a good start. We can see something now. In this case, that's just looking at a single thread within a sheet. And then we can say, okay, can we now begin to build up a three-dimensional image? But actually, we want to do this three-dimensional image, but we've got to watch over time, because as it does its washing, we need to be able to see what's going on. So as an example between the two here, on the left-hand side, the thing is being washed in non-biological powder. On the right, it's non-biological. It's missing an enzyme that's in there. We've now got a method we can actually image and see exactly what's going on. Therefore, you can alter the components that are present, and we don't have to make a whole box full of washing powder. We can just make very small samples and understand what's going on. The problem that occurred with this, though, is that when we were doing it to have an idea of this problem solving, these big red blobs start appearing all over the place. Nobody, until they'd looked at this under small scale, had seen these little bubbles. They thought the bubbles in the washing machine were very often from the stirring. And actually, by knowing that's there, you can then use those little bubbles to help you blow the fat off the material. Just by beginning to look, and you can then build up a model of how this works, you can actually do some, if you like, called real physics, real maths, to try and understand how the bubble forms, what chemistry you might then put in, or biology in terms of the enzymes that go together. And you can actually then do that and plot out, and I'm not going to go into it, but you can see that two of the curves fall really very, very quickly, and those are the ones that have enzymes that you would expect to speed up the process, and we can do this on a very small scale with very small quantities to optimize what's going on. So it just gives you an idea that by approaching the problem, the problem is how do I wash clothes at low temperatures, and you can put these bits together. What this has actually led to is we've done some computational models, we've tested new formulas, we've done simple testing in low volumes, and we can select the best. And in fact, a variation of this, which was pure science, is now being looked at in products to improve the washing. Think of any everyday product or anything that you use anywhere or anything that you'd like to have. There is a huge amount of basic research and understanding and science and problem solving that goes into all of this. You can think of any particular product, and it could go from disposable nappies, huge science and technology in disposable nappies, and they've got to be reliable. You don't think of what goes into something. I'm told that if 2 nappies fail in one bag, you will never buy those nappies again. It means 1 in a million, I think, is the number that they dare have failed. The elastic comes off or something like that. You can take any of the products that you've looked at, and the amount of detail and science that goes into them is huge. But the crucial bit behind this is when you're trying to design and think about them and improve them, the same is true for whatever sort of products, whatever sort of things that you're looking about. You've got to look at the problem as a whole. We use optical tweezers, the Star Trek laser tractor beam, and we've used that to build the world's smallest dishwasher. So if anyone's got any 2-micron, so that's 0.002 of a millimeter pieces of glassware that need washing, we can wash them for you, because we can watch what builds up on the outside of the surface, understand the chemistry, and then improve the products that are associated with it. What I've been trying to get over is you need to look at the challenge Clearly, I've illustrated it because of my background from a scientific perspective, but the comments I've made are equally applicable across all the world to big challenges. You can think of global warming. It's not a simple challenge. It's got to be broken down and then reassembled. You need to keep focused on the question that you've got, not just, oh, I can make a better thing for measuring that. Well, yeah, but is the question really to make a better thing, or is it to answer the question? I'd also really encourage people to keep as open a mind as possible. In other words, don't go, oh, no, we don't want that. No, let the person think it through. There is genuinely no such thing as a stupid question, because if the person really understands it, they should be able to explain it to you in really simple ways. So if you're doing and working at the traditional discipline boundaries, you really have to ask your other collaborators these difficult, awkward questions. What do you really mean by that? And if they're good, they'll be able to explain it in terms that you can understand that fits with your general of real expertise. The other thing, as a sort of an aside, remember there's interest even in the most mundane of products. And if nothing else, you leave this room thinking, oh, there's an awful lot of work gone into just designing something as you go out through. There's a lot of science that goes into these products, a lot of research, because it's a big challenge to do these things. And if I've done nothing else, as I was once told off by one of my, I don't actually know who this was, but I once had feedback on my lecturers, and it said, I hate this lecturer, he makes me think. Well, actually, I was quite pleased. Somebody didn't like it, but I was quite pleased. And if I've done nothing else, you leave here and you've thought about, oh, that's interesting. I wonder how they do that. What sets of skills do they need to put together to try and understand the problem? Then I hope you found it worthwhile. Thank you very much.